So the next question is, right, why should this increase bias? Now we said that, oh, this kind of regularization is a technique that would increase the bias. So now why should restricting or rather solving a constrained optimization problem over the parameter space should increase the bias is the question. Okay, and any thoughts on that? Why do you think it should increase the bias? Bias, when I say bias, it's the bias variance bias. So why do you think? Okay, here is a homework. Show that the bias of a regularized model is always more than that of the unregularized version. So I will give you another perspective of how to do this, but yeah, you should solve it. Now from an ERM perspective, I will give you another perspective from the probabilistic viewpoint. Okay, so what you should do is construct a hypothesis with some loss function, okay, and compute the bias. Construct the same hypothesis, add some regularizer function on top of it, and show that the bias increases. That's what you should show. Okay. Okay. So now equivalence between regularized ERM and map estimates. Okay, so please recall that in map estimate we seek a distribution P, we seek the posterior of parameters conditioned on data. What was the variable that I was using? T or D or whatever. Okay, I can use, let's say that we have one data point, doesn't matter. Yeah. So we expressed the posterior of the parameter conditioned on data in terms of the prior on the parameters and the likelihood of the data conditioned on the parameters. And now remember, in the map estimate, it is a Bayesian way of looking at things. We assume that the parameters also have distributions of their own, and we encode our bias in this p theta. Okay, and what happens post the Bayesian estimate is that we update our belief as it is set, right? You remember that thing, right? You come with a bias, look at the universe, change your bias after looking at data. That's what we do in map estimate. Now let us work out a case of map estimate, right? Where let's take an example, consider an example. Where P of x given theta, let us say that it is, we take that to be a Gaussian. With some mean mu theta, and we assume that we know the variance. Now if we have to do the map estimate, okay, we have to first write down the likelihood of this. Okay, what is the likelihood of this? This is L theta is 1 over n log of P of x given theta. This is what we do. We know this result, right? This will be, I will just write it as equivalent, I will ignore the constants. This will be xi minus just realize that I am doing it for the case where there are no labels. Maybe I should have done it with the case where there are labels. Shall we do it for the case with labels? Because that's what we have been looking at for the ERM at least, right? So in that case, our this distribution was the conditional of This was the distribution that we are looking at, right, the conditional distribution of y given x, and in the case of squared error loss, what did we assume this to be? I mean, see, whatever I did without the labels also has the exact same match, but since we are looking at supervised learning, we will do it. And by the way, this is an opportunity to make this statement. All the techniques that we have seen, including regularizations, are general enough that they can be applied to supervised learning and unsupervised learning as well. It's only the distributions changes. I hope that all of you know that by now, right? So this is a distribution over y, and this we assume to be h theta, right? The mean to be h theta, and this is I. In that case, this is going to be y given x and theta, and this will be so yi minus h theta of xi, correct? Ignoring all the other constants, right? This is our likelihood function that we would maximize. No, there is a minus here, right? Because yeah, so if we minimize that, then the minus will go away. The negative, because you understand what I am saying. Normal distribution will have e power minus this quadratic term, and that minus will just come here, and we maximize the likelihood, which means that we minimize the negative of it, which will be equivalent to our ERM objective, right? Now this is the likelihood term. What about the prior? Okay, suppose we assume the prior on theta to be another Gaussian distribution. Okay. Now what is this distribution over the prior? What's the random variable that we are considering here? If we are looking at distributions over prior, what is the random variable? It is theta. So it's a distribution over theta, and let's say that we assume the mean to be 0 and variance to be 1 or identity. We can do that because it's the prior that we are choosing. Okay. If you make this, then what happens to the posterior? So now p of y given x and theta, now you know that is proportional to p of y, so this is the other way around, the theta given y and x is proportional to y given x and theta, and we have p theta. And now if we look at the log likelihood function of this particular case, okay, let me call that as LR. I will have to look at the log of this, right? It will be proportional to log of this thing now, p of theta given y and x, correct? So now these has two things. This is a log of p of y given x and theta plus log of p of theta, and we know what this term is, right? We already know that this is minus yi minus h theta of xi, and what's the second term? Assumed it to be normal distribution. This will be minus theta minus 0 whole squared. Mean is 0, so it will be theta minus 0 whole squared, and the denominator is an identity. Exponentiation and log will get cancelled with each other. All of you with me, right? Okay. What is this? So what we have want to do is in map or in probabilistic treatment, the objective is to obtain theta star that would minimize this log likelihood, sorry, maximize the log likelihood, okay, or it is minimize the negative log likelihood, which is minimize right, is exactly equal to the empirical risk minimization with the regularized cost, right, which Now this implies that regularized ERM with this as the regularizer, norm 2 as regularizer, is Bayesian estimate with a Gaussian prior. That's it. Come again? Ah, there was a summation here. Yeah, here. Yeah, see, the sum is only over terms that has I index, right? I mean, there is no summation or regularizer, so it's okay. I don't have to put a bracket. Even if I do, it doesn't matter. But yeah, okay. This is the thing, right? So regularized ERM with a particular regularizer is equivalent to the Bayesian estimate with a particular prior on the parameters. Now think about it. What we are actually saying is that by putting an L2 as a regularizer, right, around 0, this is theta and this is p theta, I am actually saying that I am instructing my optimizer or the regularized DRM to choose my parameters around 0 with highest probability. You see, that is what I am saying. So any constraint optimization problem in the deterministic sense can be seen as a Bayesian estimate. All constraint optimization problems, right, are Bayesian estimates with some prior on the parameters, or rather the variable of optimization. So whatever you take, that's the way. So here if I put a regularizer which is Gaussian this way, I am saying while you choose the parameters, choose it in such a way that the probability of finding those parameters around 0 is highest. Okay. Now suppose we change the prior. Okay. Suppose we want to change the prior in such a way that given a particular subset on in the support of parameter space, okay, the likelihood or the probability of observing those parameters have to be higher than that of Gaussian. What should I do? Do you see what I am saying? The question that I am asking is, suppose I take a small support here, small subset in the support, let us say from minus 0.5 to 0.5, I get some mass here, correct? Okay. Suppose I want to increase that mass, meaning I want to say that choose the parameters in such a way that the probability of getting those parameters around 0 is higher than that of a Gaussian, a unitary Gaussian. What should I do? I will have to change the distribution, of course. To what distribution? A distribution, okay, whose mass around the 0 given a small support is higher than that of Gaussian. What is a distribution that you know of that sort? Come again? Laplacian. Laplacian is one distribution that you can choose. Okay. So now suppose p theta is chosen to be Laplacian with parameter, let us say some alpha, then the probability of parameters around mean will be higher than that of Gaussian. And this is a homework. Can you guess, if you impose Laplacian prior, what would be the regularizer function? It's L1 now. Why? It's pretty simple. Laplacian distribution is from exponential family, right? That would have a form like this. That's it. And instead of having a quadratic term in terms of parameters, it will have a linear term in terms of parameters, not minus theta, mod theta, right? Yeah, it will have a mod theta because it is symmetric around 0, symmetric around the mean. It will be e power minus mod theta. Yeah, it will be e power minus mod theta. Instead of having 2 norm, it will have 1 norm. Now you tell me, in the popular culture, right, when people teach ML, they'll say that L1 induces sparsity in the model. Now you know why? Because the prior that you are imposing in is such that the odds of finding the parameters around 0 is higher. Now L1 induces sparsity is a blanket statement, it is not correct. I mean L1 induces more sparsity compared to Gaussian is what you should say, or L2 is what you should say. L2 also induces sparsity in the sense that it is choosing the parameters to be around 0 with higher probability. Compared to that, because the fall here in the Gaussian, see if I write the Laplacian distribution on the same plot, how would that look like? It would be steeper, no? Something like this. It will be symmetric. See, on a very different note, do you know what is perceived as beautiful from the perspective of humans' eyes? Symmetry. Yeah. So reason I said is right. I mean, the moment I break the symmetry when writing a distribution, it starts looking ugly, because that's how we have evolved as human beings. So L1 with Laplacian prior. Right. So now you know why it induces sparsity. There is also a geometric way to interpret this. Any constraint optimization problem, the moment you put a constraint on top of it. See, if you draw the objective function and also the constraint function, you are seeking for only those surfaces where these two functions intersect. That is constraint optimization problem, right? Now, what sort of constraint geometrically is an L2 constraint? Huh? L2, yeah, L2 is a sphere. If it's in one dimension, it's a circle. If it's in two dimension, it's a sphere around the origin. If you make the that k to be 0, right? So now what you are actually doing is, you might have seen this figure, right? When people talk of regularizer, all they do is write this. You have some objective function. I don't know why it should be. How do I write it? It's so difficult to write. The regularizer is a sphere. It's a circle here. This is the L2 norm, the regularizer. The objective function, it can be something like this. And the contours, right? Contours of the objective function. This is the loss, and this is the penalty. And you are only seeking for those points where these two intersect. And then what happens for L1? Huh? There's a name for that geometric shape. It's a rhombus. Yeah. See, diamond is for kids. So my son calls it a diamond, no? Yeah. So now one geometric way to look at it is that if you have an objective function and a rhombus, what are the points at which they both intersect? The chances of those two figures intersecting is highest along the coordinate axis. And coordinate axis by constructions are the points in which one of the values is 0. That's why it induces sparsity. I am not a big fan of this way of looking at things at all. So to me, simply a Laplacian distribution that has its mass concentrated around 0, and that's why you are pushing it. That's it. See, now if you give this geometric interpretation, the problem is what happens if your surface is non-convex, which is the case always. Right? You should still talk of probability, right? I mean, the odds of these two curves intersecting along the coordinate axis is highest. Why? Anyway, so I mean, just for the sake of completion of the story, I just gave you both the interpretations, right? But but remember this, this is what the take home message is, that the moment you regularize, you are inducing bias with a prior on parameters. okay. And this sort of restriction can come from any way. I mean, it can be an explicit constraint on the optimization, or it can be a restriction that you do on the architecture or h theta itself. As I said, right, suppose you assume your h theta to be a linear function of data, then you are heavily regularizing this. From the functions of all possible, from the bag of all possible functional forms for h, you are only choosing the linear families. That is heavy regularization. That is why if you choose linear models, they typically underfit. Why is that? That is because by construction it is heavily regularized. You see what I am saying? So, any model choice that we make, okay, is a regularization implicitly. Now, what prior does it correspond to? You may not know that explicitly for all cases. You know, what is the prior that is imposed when you are choosing linear family of models is difficult to pinpoint. But however, remember this, that any choice that we make on the model implicitly puts bias on our on the optimization. Now, an equivalent statement would be that any choice that we make on our density function while we are doing ML estimation is an implicit bias. That is why in modern architectures or modern machine learning, the practice is to choose as big a model as possible, okay, and then solve regularized optimization problems. Last class I told you, right, the typical practice is to over parameterize and then increase the bias. This is the reason, because any restricted choice, model choice that you make, and you asked me last class, right, any restrictive choice that you make on the model is already starting with a lot of bias. So why would you do that? See, it's like this, right? We all studied biology and history and all that when we went to schools. Do we use it in our professions or anything? We don't. We over parameterize and then regularize, no? Now, if you say that, oh, I will study computer science and I will only study things that are related to computer science from day one, then you are heavily regularized and heavily biased from day one. Why would you want to do that? That is the idea. So that is why you start with, in fact, when we look at neural networks, I will give you another perspective to this, okay. See, this curve, right. So now what we are actually doing is, if we start with suppose you are solving a polynomial regression problem, let us say, right. You always choose the highest possible degree for the polynomial, right, and then use norm penalties and solve regularized least squares. Effectively, what we do is we start with this region, okay, and then we push the model back. When I say push the model back, I mean compared to the, you just have the regularized, you solve the regularized least square, that is it. Yeah. In neural network training, especially if you are doing, see, this is the case when your model complexity is defined as number of parameters and so on. I also told you in the last class that this x-axis may also mean steps of the iterative numerical algorithm that we are solving in terms of gradient descent, right. Now, suppose we are solving ERM through gradient descent or numerical algorithms, then what people typically do is that keep training or keep running your numerical algorithm, numerical differentiation algorithm or gradient descent for a very long time, okay, till your training error reduces drastically, okay. Keep tracking your validation accuracy and get this curve and ship the model at this point. You see what I am saying? So this is called checkpointing. So what you do is at every point, right, you choose your, save your parameters. So every gradient step is a new model, isn't it? Suppose you are doing EM, every EM step is a new model that you are getting. Save your parameters at all points, okay, and ship the model or choose that model as your final model at this particular point in time. And this is called early stopping, okay. Now here is the catch. Let us say that I quantify the number of gradient steps using some parameter tau, tau equal to 1, 2, 3, 4, 5, 6, 7, 8 something, right. I can show mathematically that stopping my training with a iterative algorithm at tau equal to tau naught is equivalent to L2 regularization with the regularization constant lambda defining where to stop. I mean, you can intuitively see why, right. So, if you stop early or if you ship a model here, okay, it should be equivalent to starting from here and adding some regularization and pushing it back, isn't it? It can be mathematically shown that they are mathematically equivalent. Early stopping is equivalent to L2 regularization is what you can show. Okay, right. So, this is one thing. Yeah, that was about early stopping. I told you, right. I mean, there are 3 ways to do it. Parameter norm penalty is one way to do it. Optimization procedures, I just told you. I mean, where you stop early, right. You stop the optimization early. Actually, you don't stop early because you don't know where to stop. You train for a long time, keep saving your models, ship the one that corresponds to the least validation error. In fact, that is what is done even today, right. I mean, that is how you train it. And architectural restrictions is something that we will see later in the course, right, where you take a neural network, a fully connected neural network. A convolutional neural network is a heavily regularized fully connected neural network is what I will show you later in the course. Okay. A transformer is one way to regularize any architectural design that you do. Yeah, there is one other optimization procedural regularizer that I will just mention without proving, and then we will move to the next topic. We will stop here and continue in the next lecture.